SNF for easy, cost-efficient, and sustainable EOR solutions. In a world where the energy demand continues to climb, oil extraction must be done in an environmentally responsible way. For EOR operations, this means reducing CO2 emissions. When changing from water flood to polymer flood, the water production can be reduced from 9 barrels of water to 3 barrels of water per produced barrel of oil. SNF achieves this with modular plug-and-pump installations for quick and cost-effective unit implementation with many added benefits. Polymer flooding involves increasing the viscosity of injection water to enhance sweep efficiency and ultimate recovery of oil within a deposit. SNF assists clients through every step of the process, from assisting screening and reservoir studies, polymer logistics, to on-site storage, mixing, and injection. SNF designs, implements, and operates on-site facilities for the client. Polymer flooding has a higher added value than water flooding. Due to the greater sweep efficiency of polymer flooding, the overall recovery will be accelerated with significant water production reduction per barrel of oil. Using SNF system, clients' water cut went from 90% to 70%, which means 3 times less water production per extra produced barrel of oil, savings on lifting operation and production costs. These benefits also result in a reduction of up to 3 times in greenhouse gas emissions during the operations. SNF improves the efficiency of oil production processes. Because polymer flooding is easy to implement and more mature than other methods, development time will be significantly reduced.
Uh, good morning, everybody. I'm going to. My name is Jose Maria Herrera. I am the president of the student SP Unican Student Chapter, and today I will be the moderator of this course. First of all, I would like to remind that our Kahoot quiz game is now available and will be end at noon. The prizes are incredible and it's worth participating. Check the chat or the email and access the link to play. Well, I would like to introduce our guest. It is a great pleasure that we welcome to Ross Rothbra. Before we get started, I would like to remind a few reminders to the audience. All the opinions of this event refer only to the opinions of the speakers and the participants and not of their respective companies or even the chapter. Furthermore, if there is any illusion of a discriminatory nature or reference to social, gender, or racial discrimination, the participant will be aware that he will be immediately notified. Don't forget to send your doubts and questions via chat to Ross Radbra, and he will answer them at the end of the presentation. For those who intend to obtain the certificate of the course at the end of the session, a form will be made available to confirm the present. Certificates will be issued to those who obtained 75% of the attendance according to the form. And finally, don't forget to follow us on Instagram at SPUnicamp so you can follow our activities in addition to having access to quality information. So with that, I will give the word to Professor Rosbrad. Good morning, Professor. You can share your presentation and start with your course.
Thank you very much, Jose, and thank you everyone for attending this morning. So, as an introduction, my name is Ross Roxburgh, and I'm one of the petroleum engineers at a company called Petroleum Experts. So, as you're going to see over the next hour and a half, Petroleum Experts specializes in the integration of different engineering models to capture the full field behavior, both in terms of modeling and in terms of real-time surveillance and optimization of fields. So we're going to go through some of the fundamentals this morning, how we achieve the objectives we set out for ourselves, and how our long-term goals can be achieved by having a system which allows us to maintain and sustain a solution moving forward. I'm not sure if that's saying something about that Spanish. Unfortunately, it'll have been English. I'm not sure if that's what, like, I see questions on the right-hand side. So if I share my screen. Okay, thank you, Luis. Okay. So I hope it can everyone see my screen, or can someone, Luis, can you let me know if you can see my presentation? Or Jose, sorry. I'm going to assume that you can see my presentation.
Yes, Professor, we can see your presentation here in the screen.
Fantastic, thank you. So we're going to go through an introduction, talk about what is integration and how do we achieve that integration. Then we'll talk about the value of that integration, how we sustain it through time, and that will bring us on to the digital oil field with an example at the end. So in the oil and gas industry, we have many different departments, many different units which make up our entire company. That can be the subsurface reservoir models or reservoir engineers, the surface production engineers, and the process engineers who work in the processing facilities. An integrated model is where we take the individual models that specialize in these parts and bring them together to form a single model which represents our entire system. By doing this, what we are doing is removing what we refer to as artificial boundary conditions, and we bring disciplines together to interact as one. So if I look at only a reservoir, then I don't understand, for example, the impact that water has on my ability to lift a fluid. So if I look only at the reservoir, I may see water cut increase over time, but I don't understand what's bad about producing water, which is that it makes the fluid denser, it makes it hard to lift the surface, and therefore I produce less fluid because of it. Only by bringing together the production surface models with the subsurface reservoir model can we see that together. So removing those artificial boundaries gives us a better and more realistic impression of reality. So if we take an oil field here, we have our reservoirs in the subsurface. We have wells which produce those to the subsea or to the surface for onshore. We then have pipelines and a network of pipes which bring those to our platform, where we then have facilities, and finally process, where we may split that into different components to then sell. So our almost every oil field we have has this structure in some kind or other. And therefore, looking at the system as a whole will give us a more accurate representation of what is really happening. So our overall objective, whenever we are modeling, is to try to improve our decision-making process. So we want to see sustained production increases, and we do that through efficient decision-making based upon a precision of technical strength, shared knowledge, and understanding. So the key challenge that we're trying to overcome here is a compartmentalized knowledge within our system. We may have one engineer who's in charge of or a team of reservoir engineers who understand the reservoir. They base their knowledge on a team of geologists and geophysicists who build the original reservoir system. We have production engineers who are looking at the wellbore, how that flows into the network. And then we can have specialized engineers such as flow assurance process, which are looking at given subsets. All that obviously feeds into the economics of the system, because in the end, what we're trying to do is make the most money for our company. So we're trying to have a system which builds up on this ability. And that's something which we've done at Petroleum Experts for a very long time. So we look at, for example, the strategy of integration. We want to bring together the geology with the reservoir engineers to ensure that we have the best possible reservoir model that we can. We then use that reservoir model along with our production system to couple that and understand the impact that the pipelines and the well bores, compressors and pumps, etc., have on our production from the reservoir. And then also we need to consider the process and the economics of that process. By looking at the whole picture, we begin to see the true value and understand the opportunities that we have. We can look at the system as a whole and look at things such as global optimization. So how do I produce from my field to optimize my production or optimize my revenue on a global basis? Additionally, we need to have a way of managing these systems altogether. It's all fine and well as saying we want to look at the entire process, but actually be able to do that is a lot more difficult. And that's where our tools and our technologies come in. So to give you an idea of how we got to where we are today, our company, Petroleum Experts, was founded in 1990. And its founding principle was integration, bringing together the reservoir, the wells, and the process. And this was done through our main Petex modeling tools, what we call the IPM modeling tools. So that's a program called PVTP for fluid characterization, MBAL for material balance reservoir modeling, Prosper for well modeling, and GAP for service network modeling. As time went on, technology advanced in terms of numerical simulation, and vendors started to want to attach our integrated models to other vendors' tools. So that could be, for example, reservoir models such as Eclipse or CMG. It could be process simulators such as Pro2 or Unisim, HYSYS, or it could be economic packages such as Excel. So this advanced integration platform we brought on in early 2000 called Resolve. That allowed us limitless scope in connecting tools to whatever tool fits best for our client can now be brought into the overall picture. We also developed our own numerical simulator called Reveal. Inside Resolve, we then had to be able to make the models do what we wanted them to do. So if I'm running a 20-year forecast to understand how much my field will produce, we have to be able to model not just what happens in terms of the reservoir depletion and my wellbore, but also the management and field decisions which are made through that time. And therefore, we introduced a way of controlling the models called visual workflows. These essentially allow us to make the models take decisions based on what is happening with them. So, for example, if I have 5 wells, but on year 1, I'm only producing from 2 wells, I can say, I only want to bring on my 3rd well if my production rate drops below a certain target. So if my production rate drops below 1,000 barrels per day, bring on well 3. That will increase my production again until perhaps at some point in the future I bring in well 4 and well 5. So I can bring in logic to help me calculate when new pieces of equipment or new wells are going to be required to meet my conditions. That's done through the visual workflows. We also start to look more at real-time systems. So rather than just trying to plan for the future, we also want to understand what is happening now. That scope we'll talk about later on in the presentation, and we call this the digital oil field. As time went on, we began to add even more technologies such as structural geology into our suite, and also transient network and transient wellbore modeling tools. Altogether, through time, we now have a set of tools and calculation engines which allow us to solve pretty much any problem in the oil and gas industry today. Now, that doesn't mean the tools solve it for you, but what this means is it gives you a platform where you can solve it yourself. And that's the key to what we do. We deliver platforms which allow engineers to do their jobs better. In no way are we trying to replace engineers, quite the opposite. We give engineers more power to do their jobs. So we've spoken about the idea of integration, but it's always a good idea to show a case study to show the dangers of not looking at integration, and indeed, therefore, the value that integration brings. So why is integration so important? This is a case study from West Africa. This was a case study from, I think, the late 1990s, but we still see this commonly even today. When we got involved in this project, the current production in the field was about 160,000 stock tank barrels per day. They were producing that from 118 wells across 38 different reservoir units. Now, in order to produce these wells from these different reservoirs, they connected them all through different pipelines, and we had pipelines, compressors, and separators all within the network. So it was a very complex surface network they had. The objective of the company was to increase production by about 30%. So they wanted to go from 160,000 to 210,000 stock tank barrels per day. So how did they approach this? Well, this was back, I said, in the 1990s, and therefore the study was done using only a reservoir model, but they were using an advanced numerical simulation model. So they had a simulation model of the reservoir, and the conclusion of this study was if they drilled more wells, they would get more oil. That seemed to make sense. So they went ahead and they drilled new wells. They spent over $200 million drilling a series of new wells in the field. They tested each well. The wells were drilled well. They were producing the oil they thought. Yet, when they added it to the system, they saw no increase in production. The question was, well, why did this happen? And could integration help us understand why it had happened? So they came to us at Petroleum Experts and they said, can we use integration to help us understand why our new wells are not helping? So we built with them a gap model. So the gap model contains reservoirs, which are represented by these small semicircles. Green is oils, Yellow is retrograde condensate, and red is dry gas. So you'll see there's a mixture of different reservoir types. We have well models. That's these small triangles. So again, red triangles are gas wells, green triangles are oil wells for the primary phases. We have pipelines, the little blue rectangles. We have inline separators, and we have compressors. So you'll see everything which is required to capture this system is within the model. The reservoir, the wells, and the surface network, including the compressors, separators, and pipelines. So this integrated model is then used to say, well, what happens if we run this model? And what we found when we ran this model was that this pipeline here, the very last pipeline, which is used to transport the fluid from the field to the process facilities, was at maximum capacity. So essentially, if you look at this line, if the field has a pressure rate relationship with this blue line, because of that pipeline, it limited the rate to this red line. So even if we reduced the pressure, we got no more rate. This red line, the diameter of this pipeline was restricting production. It doesn't matter how many wells we add upstream, we cannot push any more fluid through this pipeline. Therefore, the solution was to add a second pipeline in parallel to the existing pipeline. By adding a second pipeline, we're able to increase the capacity of this flow rate and produce more from the field. In fact, they found that they did not have to drill a single new well. All the new wells that they drilled were not necessary. And if on day one they had added this pipeline, they would have reached their target straight away. So why is this important? This is important because it's trying to show us the problem of looking at only a small section of our system. If I look only at my reservoir, I see only problems and solutions within my reservoir. Equally, if I looked only at my well or only at my pipeline, I'm only going to see the problems or the solutions in the pipeline. So in this case, the problem was in the pipeline. But in other cases, it could have been anywhere in our system. The key conclusion is unless we look at everything together, we will not necessarily find the right answer. And therefore, a single integrated model which captures the total behavior of the system is the only way we can allow engineers to make rational decisions. If we're making good decisions, we should be adding value to our field. This is true both for new developments and for existing fields. For new developments, it's about forecasting what will happen in the future and avoiding surprises, while for existing fields, it's about understanding the true bottlenecks and the true performance of those fields. So integration facilitates rational economic decisions, which is how we add value. Now, we showed you briefly there this model. All the models in this, or all the individual programs in this model are all provided by ourselves at Petroleum Experts. However, sometimes we need models made by third-party vendors, and therefore we have to look at solution formulation beyond just Petroleum Experts' tools and out into the wider world as well. So we've already spoken about the power of integration in terms of understanding the complexities of the entire system. Only once we understand how the whole system behaves can we begin to talk about optimization. If I look only at one well, then I can find the maximum oil rate of this well, perhaps by increasing gas lift gas rate. That's not optimizing my field, because maybe that gas lift gas would be better used on another well. So we can only talk about optimization when we understand the impact that a decision or a change has on the entire system. So we also need, we mentioned earlier, to honor constraints and also field management rules. This is done through logic and workflows. In other words, if we want to have a truly integrated model, we need to have a specific tool, which is an integrator and a controller, which will take control of the integration, optimization, and the logic of our production. The role of this within the IPM suite is resolve. So the first aspect that it does is it integrates tools together. Then it brings in advanced optimization algorithms to try to control the fields. And then third, it allows us to formulate solutions using the logical visual workflows operations. So what do we mean by solution formulation? A big part of our job at Petroleum Experts is helping our clients to solve issues that they have. And we do that by helping them form solutions. So solutions are how we are going to achieve the objective that they have. And we formulate this by going through a systematic scientific process. So whenever we're approaching a new problem, we have 3 steps. We want to understand the problem or the current conditions, reproduce the current conditions, and then predict and optimize a better solution or a better setup. So using Resolve, we can begin to do a lot more than just integration. So here, for example, we have 6 different reservoir models linked to 3 different network models. In this case, a production system, a water injection system, and a gas injection system. All the production from our network model goes into a process model going forwards. So this is integration. However, Resolve does a lot more than just that. Once we can connect to applications, we can also use visual workflows to control those fields. We can use calculators to perform additional calculations, such as hydrate calculations, scaling calculations, stability calculations, to try and help us manage our fields better. This allows us to increase the value through time. So we start with the physical models. These obtain a good amount of value, but by themselves require a quite high amount of maintenance to keep in a solid state. If we integrate those in with the physical, operational, and management constraints of the system, then that gives us more value, because now our physical model understands the challenges. It knows, for example, how much gas lift I have, what the ESP constraints are, if there's routing optimization to be done. So the value increases, but so too does the maintenance, does the effort levels. Adding optimization algorithms to find the best solutions increases the value substantially, doesn't really change the effort. The maintenance effort remains the same. However, we also need to have a way of increasing or decreasing the maintenance effort. So the use of visual workflows allows us to basically reduce the work we do while achieving those same objectives. However, the final step is to integrate that in with a real-time system. So use online data along with field management in order to get even more value out while also reducing the maintenance effort. So you'll see, while we got a lot of value out of the models standalone, they were a lot harder to maintain when you have to do all that work yourself. By using workflows and online data, we can increase the value, but also, more importantly, decrease the time the engineer is spending updating models, validating models, doing this work which we can take out of their hands. So this is now all done within the IPM suite and into what we call the digital oil field. So how do we do this through time? We have this idea that as I gain value, I also want to reduce the effort required. So how do we sustain value through time without spending all of our time sustaining that value? We do this through what we call a digital oil field. The digital oil field fundamentally is a digital representation of our oil or gas field on a computer. The system allows us to reproduce the physical behavior of the field using models, test different scenarios and different options in order to optimize production and extract the maximum value from the field. This could be short-term production increases, or it could be long-term recovery increases depending on your specific objectives. To give you an idea of our technology, Petroleum Expert's DOF technology is mature and is used by over 250 different oil fields around the world. Now, the key to our technology is that while every oil field is different, every gas field is different, the technology that the clients use is always the same. So we use the same architecture and the same software products to solve all these different problems. However, the way that we configure the software will change depending on the situation. Fundamentally, we're using the same tools. And over 450 companies worldwide are using this technology to help them out. So in terms of our digital oil field, what are we trying to achieve? And just like we said for our integration, our objective is measurable and sustained improvements in our field production. How do we achieve that? The first step is to understand how our field is performing. Before we can say how do we improve it, we first need to know where are we doing and how are we doing now. This is done through monitoring of data, surveillance of the production, and diagnostics of that surveillance. We can only do surveillance if we can reproduce the reality on the basis of our understandings. So that means that can our models reproduce what we see in the field, creating our benchmark. Once we have a model that can reproduce what's happening in our field, we gain more confidence in it. And that confidence allows us to use it for jobs such as optimization, improving field performance. How can I change my field management rules in order to produce more oil or more gas from my field? Alternatively, we can use it to see how the field will behave under different conditions. Perhaps I know that next month I have a planned workover on a set of wells. The question may be, when those wells are shut in to perform maintenance, how should I produce my other wells to reduce the total drop in production as much as possible? So what if I do this? What is the best I can do? The above allows us to make quick, rational decisions and hence add value to our field. So this is what we're trying to achieve from our systems. But there are a number of challenges that we face within this discipline. We've already discussed in some detail the competing and contradictory demands of different disciplines. My reservoir engineers, my production engineers, and my process engineers may have different ideas in terms of how they want to produce the field. A classic example would be an ESP, an electrical submersible pump. If I put a pump in the well, then my reservoir engineers or my production engineers may want to run that pump at as high a frequency as possible in order to produce as much oil and gas as possible. However, the engineers in charge of the pump, perhaps the maintenance engineers, do not want to run the pump at full speed, because the harder you run a pump, the more likely it is to fail. And therefore, the more likely it is it needs to be replaced. So there needs to be a compromise between those two demands. If you talk only to one team, you'll get the wrong answer. You need to speak to both teams, understand the challenges, and then decide what the best solution is from there. We've also discussed compartmentalized knowledge of different disciplines. We also have geographic and demographic challenges. The engineers making the decisions may not be at the field, and therefore they may not be on site. So the ability to see what's happening in real time from wellheads, from pipelines, etc., is very useful if you're geographically in a different location. We also need to make sure we have access to the correct information, reliable information, in order to make these efficient decisions. We want to understand the uncertainties associated with that information, as well as understanding the resources and difficulties in maintaining any technology as we proceed. So we have our objectives, and now we understand the challenges that we have to overcome. These challenges are what drives us in terms of our digital oil field or DOF development. The vision that we have with this technology is the idea that by sharing understanding and sharing knowledge, we can improve the company as a whole. My understanding as an engineer in charge of one well should be the same as the understanding from the engineer in charge of the network, should be the same as the engineer in charge of the field, is the same as the understanding of the CEO of the company. Different teams have different objectives. However, we should all share that same understanding of the system so we make the best decisions together. If the optimization team understands something more about the system, they feed that into the enterprise level so everyone else can benefit from that new understanding. That sharing of the data, sharing of our information is what gives power and what gives value to everyone in the company, from our management, looking at data and reviewing our system, to the operations and the field who actually get that oil and gas out of the ground. It's important for us that technology is an enabler. By that, we mean technology should be helping the engineer, not replacing the engineer. So how do we do that? Well, first, we need to overcome the coherent and multidisciplinary understanding of the field. And that's addressed using integrated production modeling. So we've mentioned that in the previous slides, how we use a single model approach to capture the entire behavior of the field in order to avoid missing any one department's information and understanding. But we actually cause ourselves a problem when we do that. By having one model that everyone shares, we need to have a way of managing those models and sharing that understanding in one place. So we need to have a model management system where different people can change different models. We have version control, which allows us to see who has changed what and when, and ensures that whenever anyone needs a model, they know exactly where to go to get the most up-to-date model today. If they want a model from last month, they should also be able to access the model that was valid last month as well. So that model management is very important. We need to be able to rationalize the use of our understanding and knowledge for the field and create best practices to share them. If you're a new graduate joining an oil and gas company, you know there's people working with you who have 5 years, 10 years, possibly even 30 years experience producing oil and gas, possibly from that field or from other fields like it. So if we do this correctly, we can set up the system so that the understanding that's been developed over 30 years by the senior engineers can be used to create best practices, which then the youngest engineers who have the least experience can still follow. That will hopefully allow that knowledge and value that the older generations have to be passed down to the younger generations so they can also benefit from it. And that's an incredibly important part of sustainability. We use, in this case, engineering workflows and workflow management to achieve this. So an engineering workflow is essentially a series of steps that will use models with data in order to calculate results. Those results can then be used in the analysis to understand how best to produce the field. So these workflows can range from everything from virtual metering, so estimating the production of each well, to gas lift troubleshooting, to estimate the depth that we're injecting at or the rate we are injecting into each well, all the way up to optimization, how each well should be choked back, what frequency each pump should be running at, and how much gas lift gas each well should be achieving. So we can build up these workflows, and these workflows essentially encapsulate that knowledge. Finally, we need a location, a place where every engineer can go to, where they can see the information that's available and use that information to make decisions. That one portal, that one place, needs to integrate together dynamic information, static information, and calculated information. Calculated both from models and from data-driven models. So physics-based and data-driven are important for our systems. So a system needs to look at all these different elements together. To achieve this, we believe at Petroleum Experts that the solution needs to be a product. That means that this is not something which is different in every company you go to, but it's something which is sustainable, upgradable, extensible, and scalable. It requires no programming from the user's point of view. We instead use visual workflows, and we've put as much work into it as possible to make it as user-friendly as possible. This is done by providing out-the-box functionality to address the most pressing and common concerns within the oil and gas industry. So this can be things like well test validation and the PVT checks that go along with that, well surveillance and virtual metering, quality control of any piece of equipment from a compressor up to a choke, the total system quality control, and then value-added tasks such as optimization, forecasting, with and without optimization, and many, many more flow assurance calculations, etc. We also have a number of templates which allow us to build up our visualization very quickly within our projects. So hopefully that's given you now an idea of the overall objectives and how we're going to achieve it. The last step before demonstration is to show you the components of the system. How do we actually achieve these objectives? We start with our physical models. These physical models, the integrated production models, form the basis of everything that we do at Petroleum Experts. And really, these give us two main things. The physical models give us the ability to capture the physics and answer the what-if questions. So the advantage of a physics-based model is once calibrated, because it's based on physics, if we change the conditions of the model to things which have never happened in the field, we can still trust the model to give us physical results. So if I have produced no water in the life of my well, I can still use a physics-based model to say, if I start producing water, here's what I expect to happen to my IPR, or my reservoir performance, my well performance, or my VLP, and how that will affect my total rate. So only using a physics-based model can we extrapolate, or not extrapolate, can we model outside of our known experiences. Once we have a model that can capture what happens when I change things, I can begin to use optimization algorithms to say, well, what's the best thing I can do? If I do start producing more water or more gas, which well should I choke back to still meet my oil constraint or my oil target within a given liquid rate constraint of my system, or a given gas rate constraint of my system? So optimization algorithms need to understand what happens if things change, and that's what the physical models provide. Now, within a real-time system, we don't want to have to run every calculation ourselves. So the next stage is to have a series of real-time workflows that can run either on a schedule, that's on a real-time basis, on demand, so when we want them to run, or based upon events in the field. So the engineering workflows are essentially our way of telling the models what we want them to calculate. Based upon those calculations, we may do further calculations, or we may simply show the results up to the users for the final results. Depending on the size of our field or the number of calculations we perform, we'll probably need lots of computers to run those calculations on. We call those computers clusters. The clusters essentially act to give us more availability of calculations. In addition to engineering calculations or engineering workflows, which use our physics-based models, we may also have data-driven workflows or processes which we also require. So that can be from simply translating one value into another through a conversion plot, for example, going from a choke travel to an equivalent choke diameter, to something far more complex like neural networks, machine learning, AI, which use real-time data to give an output. So we have both the ability to look at engineering workflows, which use our physical models, and data-driven models, which use models but don't require the physics-based models, are driven more by data, big data, science, etc. Okay. Regardless of these workflows, we need to have data coming into our system. So this can be from real-time historians, well test records, or static data such as PVT reports, logs, completion diagrams, etc. Either way, we need to have a way of managing that data when it arrives, processing it, and making it available to everyone who needs it. Finally, we need to have a way for the engineers to interact with our system. No matter how good your calculation is, if people don't understand the context and are able to interact with it, there is no value from it. So we need to be able to expose the results for our calculations and display it in a way that gets the most value for the engineers. We do that through what we call the visualization or engineering portal of our system. So together, this system is what we call the digital oil field, and it's made up of three main components. Model catalog, which is in charge of the model management of our physics-based models and any static data that we have. IFM, which is the workflow manager. It's in charge of coordinating the engineering workflows in our system. And then IVM. IVM has two roles. One, IVM is the data manager. So it's in charge of talking to the outside world, bringing data in from outside, and also running all the data-driven models from within it. In addition to the data manager, IVM is also our visualization or engineering portal. So it's where the engineers interact with the tools. It's where the engineers can view the results, plot the real-time data to understand what is going on. So that forms together the different layers of our system. Each one is specifically designed to solve one of the challenges that we previously had. So the model catalog is our model management system. Here we can track changes in models, limit who's allowed to change models, and ensure that at any point in time we know which is the current most up-to-date model. IFM, because it's in charge of the workflow management, is trying to basically process and manage those workflows that represent our best practice. That allows the engineers to follow the same process, for example, to analyze a well test, regardless of how long they've worked in the field. And then finally, IVM gives us that platform for visualization and interaction with the data, as well as managing the data and ensuring that everything that we need is available in one place. So to give you an idea of how that works, maybe I have some real-time data in the field. Perhaps it's a wellhead pressure. That wellhead pressure comes into the field through the data management layer. Maybe I just want to view that real-time data. So maybe I'm an engineer who just wants to look at what's my current wellhead pressure, how's it changed over the last week. I can view that raw data so I can understand how it's changing at high frequency. But I may also want to pass that into a workflow which changes the high frequency into a low frequency. Here we can perhaps remove some noise from the surroundings, some slugging effects, etc., and see instead what's the representative changes in these values. I can then take that data, either the raw data or the process data, pass that down to an engineering workflow that will pick up a model from my model catalog. Right, wrong direction. And it will send that workflow with that data and the model out to a cluster. Now, if I have 3 wells, perhaps I want to spread those calculations across 3 different computers to make it faster. Alternatively, if I have 1 well but 3 calculations, perhaps I want to spread it out that way. So there's many reasons why you'd want to separate out these jobs. Once the calculations are completed, I have some results. Those results can get passed back up to the data manager and passed up to the visualization. So now, for example, the engineer who's looking at the raw data can also look at calculated data to say, as I change my wellhead pressure, what effect did that have perhaps on my flow rate of my well? Alternatively, we may find that the results of one calculation become the inputs to a second calculation. So if our downhole gauge pressure breaks, so we have no way of measuring what's happening downhole, I could use a model to calculate what I believe is happening downhole, and then that might result of downhole pressure may get passed to a separate reservoir calculation to say, if this is my bottom hole pressure, what's happening in my reservoir? So the results from one workflow can be visualized, but also they can be passed into another system. So what I'd like to do now for the last kind of 15, 20 minutes that I'm going to speak today, I'm going to do a live demo of such a system so you get an idea of how this looks in reality. So this, you can now see on the screen, is what we call IVM, which is our visualization. That's the top layer of what we were just showing you. This is the visualization part, which allows us to see what's going on in our system. So here, for example, you'll see we have an oil field. Each one of these dots represents a different well, with green being flowing and red being shut in. So I can see that all my wells are currently flowing in my system, which is fantastic. On the right-hand side, I then have the total oil, water, liquid, gas lift rates across these 4 subfields. So you'll see there's one field of these 4, a field down here of 2 wells up here forming a field, and then 5 wells over here forming my last field. So each field has a total, and I can see that in the bars, but also in the pie charts beneath it. So this shows me the Powder Hole field is producing my most, while the Logie East is producing my least. But it also allows me to see that while Logie East is producing the least in terms of liquid, you'll see Spectrum is producing a lot of water. So a lot of water is coming from Spectrum, especially compared to the amount of liquid it is producing. I can also begin to look at the wells on an individual level. So now I'm looking not at the field totals, but at the individual well totals. So each well has now an oil rate, water rate, liquid rate, gas rate, and now water cut and GOR provided. If I click on some of these tabs, I can click on water, which you'll see now shows the bubbles relative to the size of water rate and changes my order to see where most of my water is being produced from. I can do it on liquid rate, gas rate, or even water cut to see where that's coming from. So all this is doing is showing the same information in a different way. My bubbles change to change these values, and the table is ordered based upon the unit that I select. IVM is based on what we call a drill down visualization basis. So we start at the highest level, and what we show is the information that the company feels is most important. So if I'm the field manager, maybe what I want to see is how much is my total production, which I see here, and also maybe down here, how is my current oil rate compared to my optimum oil rate? And you'll see I'm slightly below. So this tells me that I could be producing a higher oil rate if I change the controls. However, if I'm a field engineer, perhaps I'm more interested in a particular well. So now I can drill down deeper. So I can go from the field to a particular well. And here, for example, you'll see I now have a certain well in the field. The well has got a name. On the left-hand side, I have all of the real-time data which is available. So, for example, I can plot my wellhead pressure and my flow line pressure. If I plot these, I can see how these have changed through time. So you'll see for the last few days, I have a pretty steady wellhead pressure and flow line pressure. If I bring up a cursor, I can try to see what is the pressure drop across this choke. And you'll see the pressure drop across the choke is approximately 25 to 25 psi. So that's by going from this real-time data, I can very quickly see more information about things like pressure drops, etc. I could bring in my downhole gauge. Now I have the downhole gauge pressure as well as the wellhead, and I can see the pressure drop inside my well. Is much larger. So here between my downhole gauge at the bottom of my well and my wellhead, the fluid is seeing a pressure drop of about 2,430 psig or psi. So again, this is useful. Perhaps I'm looking through time. How has this changed? Then I can look at why has it changed. So this left-hand side is all about the real data and how things are changing in the field. The right-hand side here is all about calculated data and using this information, which is easy to measure, to calculate things which are not so easy to measure. So you'll see here, I'm measuring pressures and temperatures. On the right-hand side, I have oil rate, water rate, gas rate, water cut, GOR. So these are things which are not as easy to measure, and therefore we often need to calculate them using the information which we do have. We call this well surveillance or virtual metering. Well surveillance uses the principle that there are many different ways to calculate the same thing. I can look at my total well. We call that the VLP IPR. I can look at the pressure drop between my wellhead and my downhole gauge. We call that the VLP. We can look at the pressure drop between the downhole gauge and the reservoir. We call it the IPR. Or we could use the pressure drop between the wellhead and the flow line, which we call the choke rate. So each one of these calculations uses different boundary conditions measured in the field, and that allows us to calculate the flow rate in different ways. Hopefully, as you see here, if we have a good model, all these different calculations should give approximately the same answer. You'll see here, they're not exactly the same, but we're going from about 7,000 for choke up to about 7,100 for our VLP IPR. So these are all very nice and close together. See here. And therefore we can say with pretty good certainty, we know how much this well is producing. If these were giving very different results, then I'd have to look more into my model, what's going on, and then work out what to change in order to make them all agree to have that better understanding. I can look at how I got these. So things like my well rate estimation shows me my IPR curve, my blue line, with my VLP curve, and where these two curves intersect, give me this VLP IPR method. Whereas my choke performance is based upon a choke curve. And here you'll see I'm operating down here. Because the pressure drop across my choke is small, there's a far bigger variance in the results because it's a far more unstable or far more sensitive portion of the choke curve. Hence why the pink line jumps up and down a lot more, because it's a more sensitive calculation in my choke where it is. So all of this gives me the ability to say that I understand this well very nicely. And I'm happy that the production rates, the water cuts, the GORs, the reservoir pressures and PIs must all be approximately correct, because I'm getting a very good match on this data. In some other wells, I go to P2, you'll see I don't have as good a match. Here, my different rate methods, VLP IPR, VLP IPR, and now we have this extra method called casing head pressure. These are all showing different results. Well, two of the three are, I should say. Why is that? In this case, it's because the IPR curve we're using has not been updated recently. So the IPR essentially is your ability to produce fluid out of your reservoir. And for an oil well, it's based on two main things: the pressure of your reservoir and the productivity of your reservoir. Now, in this case, we're quite lucky because we have an external rate method. So we're actually measuring the liquid rates. And you'll see we have quite a good match on the casing head pressure and VLP pressure for that external rate, which is good news. Okay. However, what's wrong with it is the reservoir pressure is a lot lower. So in order to get these models to match, we would have to have changed the reservoir pressure. So this basically allows us to track in real time how certain properties change. Those properties can be things like the reservoir pressure, the water cut of the well, the GOR of the well. So when these don't agree, it's a very useful diagnostic tool to try to estimate what we think is changing. And we use that to increase our understanding of the field. When we increase our understanding, we give ourselves more value. So once we're happy that we have a good monitoring of the field, we're happy we understand how much each well is producing, we can then look at tasks such as optimization. So optimization is trying to produce more oil or more gas from our field. And we do that following different optimization criteria. So that could be looking at, for example, can I distribute gas lift better? So if I click on my gas lift wells, I can begin to say, is there a way for me to distribute my gas lift to give me a better performance? Or for my ESPs, within my constraints of up thrust and down thrust, can I increase my frequencies in order to get more out without breaking any constraints? This allows us to see exactly what is going on. And that's very important for our field. So what we see here is, according to our models, we can increase production by 25%, 26% by changing things like our ESP frequencies to their maximum values, because we're not in danger of exceeding any of the pump constraints. So this gives the field confidence that they can use this data to improve the system. So this is our system as it is. And this allows us to go through for everything from surveillance through to optimization. We can now take this recommendation from the models, put it into the field, and increase the value of the field that we see. So hopefully that little demonstration will give you an idea of the kind of systems that companies use in the field in real life, how they use them to get value out through things like optimization. So just to conclude the presentation before we open the floor for questions, we petroleum experts over the last 30 years have pioneered the concept of integrated production modeling in order to create models that are representative of the entire process, bring disciplines together, and eliminate boundary conditions. That allows us to make rational decisions and therefore add value. The value of the hydrocarbon fuels is maximized when we're able to see these big pictures. However, sustaining that value through time is most easily achieved when we use a digital oil field, like you've just seen. That allows us to combine the physical models with real-time data to make quicker, more efficient, and more robust decisions in the field. The faster we can make a good decision, the sooner we'll see the value of that decision. And companies around the world use our technology to achieve exactly that. So thank you very much for listening to my presentation today. I hope you have all found it valuable, found it useful. I will open the floor now for questions for the remaining 15 minutes. But if anyone has questions in the future, please don't hesitate to drop us an email at the email addresses that you see there, and we'll try and help out wherever we can. Jose, I'll hand back to yourself. Jose, I think your connection may be a little bit bad, or either mine is bad or yours bad. I can't. I can see you, but I cannot hear you, unfortunately.
Hello, thanks for your presentation. Sorry because my internet was too bad, so I tried to connect with the mobile phone. Okay, we're going to continue with the question. I don't know if someone in stream has some question here. or Dario, uh, you can manage with the chat in YouTube. You can see if we have some question there.
I don't see any questions at the moment.
Eh, there are no questions. No questions.
Here, Joan Marcos have
Oh, hi.
one.
Just to let you all,
We're going to wait here to write the question, and we can see.
just like to say that if
Here,
anyone has any
Joan
questions in
Marcos
Portuguese, please feel
is
free.
asked about the behavior simulation. How precise your software can achieve the result of simulation of others, which take a long time to have results?
So numerical simulation is an interesting subject because numerical simulation is essentially educated guesswork. We build up the best model we can with very limited information on downhole. All the other information we have of what happens downhole is what we see at surface. So the best data we have for reservoir simulator is the production data, along with the geological data that we start with. So there's a big uncertainty that goes into numerical simulation. Fundamentally, all numerical simulators use the same technology, which is solving diffusivity on a numerical basis, a Darcy flow between blocks of material bounds. We can connect to any simulator in the industry. So the key to our integration is the ability to link to any simulator that the client wants to connect to, so they can use any of the existing software out there. We do also provide our own. The key of our own technology is that it focuses on what's called the specialist study aspect. So Reveal looks at things like thermal modeling, the impact of temperature. Once you capture temperature, you can also look at things like stress fields, how the stress fields change over time due to, for example, water injection. And then we can begin to look at fracture modeling and rock mechanics in general. So we are like things like rock mechanics, water chemistry and scaling, filter cake buildups, polymer modeling, these more advanced physics-based models. Reveal is a market leader in this technology. It's something that we've been doing for over 20 years now in terms of these studies. And that's what kind of makes our simulator different to other simulators. If you've got nothing particularly interesting going, if you like, so there's no water injection, there's no chemistry effects, no mechanics effects, then most simulators will give you the same results because they're all solving Darcy flow for the same input. The value of our own simulator is integrating the specialist studies in, but the key to the integration in general is that we can link to any simulator, which is in the industry, depending on what our client would prefer to use. I hope that helps answer that question.
Okay, thanks. I think we don't have more questions about the presentation. It was a great one. So we, as SP Unican student chapter, we thank you for your time for give some sessional lecture. So, also to Professor Luis Lamas to have the time to respond make it this possible. So we're going to finish for this activity, and we also thanks to the audience to help to this project grow up. So don't forget to play the Kahoot game that will be enclosed in 2 hours. So thanks to everybody. And Dario, you can put the videos for sponsors.
Thank you, everyone.
Thank you.
everyone. See you.
SNF for easy, cost-efficient, and sustainable EOR solutions. In a world where the energy demand continues to climb, oil extraction must be done in an environmentally responsible way. For EOR operations, this means reducing CO2 emissions. When changing from water flood to polymer flood, the water production can be reduced from 9 barrels of water to 3 barrels of water per produced barrel of oil. SNF achieves this with modular plug-and-pump installations for quick and cost-effective unit implementation with many added benefits. Polymer flooding involves increasing the viscosity of injection water to enhance sweep efficiency and ultimate recovery of oil within a deposit. SNF assists clients through every step of the process. From assisting screening and reservoir studies, polymer logistics to on-site storage, mixing, and injection. SNF designs, implements, and operates on-site facilities for the client. Polymer flooding has a higher added value than water flooding. Due to the greater sweep efficiency of polymer flooding, the overall recovery will be accelerated with significant water production reduction per barrel of oil. Using SNF system, clients' water cut went from 90% to 70%, which means 3 times less water production per extra produced barrel of oil, savings on lifting operation and production costs. These benefits also result in a reduction of up to 3 times in greenhouse gas emissions during the operations. SNF improves the efficiency of oil production processes. Because polymer flooding is easy to implement and more mature than other methods, development time will be significantly reduced.